Welcome to the Climate Hour. I'm your host, Bob Grove. Today we're going to talk about how melting ice sheets are drowning the world. Since 1975, an estimated 9,000 gigatons of ice have melted from ice sheets and mountain glaciers. That's an ice block the size of Germany or Montana, with a thickness of 25 meters, 83 feet. That's taller than an 8-story building. All of that huge ice block melting has increased sea levels 4 to 6 inches since 1975. That's around 13 centimeters. If we continue today's current level of global warming, which is 1.2 degrees Celsius, if temperatures stay where they are today, we can expect a sea level rise of at least 1 to 2 meters. That's our best case scenario, 3 to 6 foot of sea level rise. And if countries continue to ignore their Paris Climate Accord contributions, the world is looking at a 2.5 to 2.9 degrees Celsius temperature increase, which will certainly lead to the collapse of the Greenland and West Antarctic ice sheets and a 10 to 12 sea level rise. That's 40 feet. So 3 to 6 feet of sea level rise if we really work on it, 40 feet if we continue business as usual. And what if we drill, baby, drill? What if we throw caution to the wind and revert to full dependence on fossil fuels? If we do that and all the world's ice melts, the general consensus is that sea levels will rise 60 to 70 meters. That's 200 to 230 feet. So let's go back to our best case scenario. Under that, many of the roads in the Florida Keys, they're actually expected to be underwater this year. Cities like Miami, New Orleans, Bangkok, Amsterdam, Basra, Georgetown, Ho Chi Minh City, and Kolkata, they're at risk of being submerged by 2030. Jakarta is already 40% underwater and may be totally submerged by 2050. Nations at risk of being uninhabitable by 2100 include Kiribati, Tuvalu, the Maldives, the Marshall Islands, and Nauru. The countries most at risk from rising sea levels in coastal areas is the United States, China, India, Japan, the Netherlands, Thailand, Vietnam, and Bangladesh. A mere 20 centimeters, just 8 inches of sea level rise, will cause at least $1 trillion a year in global flood damage to the world's largest coastal cities. The best case scenario of 1 to 2 meters sea level rise is going to displace 250 million people. And that 10, 12 meters sea level rise we talked about, that would move 1 billion people. 1 billion people looking for new homes, food, jobs. That's 11% of the world's total population, 13% of the world's urban population. So sea level rise is going to be our biggest long-term impact of climate change. And every fraction of a degree of global warming we can avoid slows down sea level rise and gives us more time to relocate the hundreds of millions of people affected. We're joined today on Zoom by Dr. Richard Alley. Dr. Alley studies glaciers worldwide. He's a member of the U.S. National Academy of Sciences and the Royal Society. He's been awarded the 2025 U.S. National Medal of Science, and he has served with the Nobel Peace Prize winning United Nations Intergovernmental Panel of Climate Change. Richard is the host of the PBS TV miniseries Earth, the Operator's Manual, which is actually based on his book of the same name. And he's been awarded Phi Beta Kappa Science Award for his book, The 2-Mile Time Machine, Ice Cores, Abrupt Climate Change, and Our Future. Hi, Richard.
Greetings, Bob, and greetings to your listeners and viewers.
Dr. Andrea Dutton is a geologist who studies past sea level change with an emphasis on the behavior of ice sheets during Earth's previous interglacial periods. Dr. Dutton is a MacArthur Fellow, Fulbright Scholar, Geological Society of America Fellow, and was acknowledged by Rolling Stone magazine as one of the 25 people shaping the future in tech, science, medicine, activism, and more. Andrea emphasizes the importance of climate communication in her public speaking events, including her TEDx talk, and in the Nova documentary, Decoding the Weather Machine, which was nominated for an Emmy in 2019. Hi, Andrea.
Hi, Bob. Great to be here today.
Dr. Paul Bierman is a geoscientist and professor of environmental science at the University of Vermont, where he develops methods to date ice and rocks. Dr. Bierman has published in Science and Nature, and his findings have been covered by CNN, the New York Times, the Washington Post, the Weather Channel, among others. Paul's latest book, When the Ice Is Gone, is an environmental history of Greenland, focusing on climate change as deciphered from an ice core collected by the US Army. Hi, Paul.
Hi, thanks for having me.
Paul, your book is based on an ice core taken by the US Army in what, 1966?
They
What
started
was the,
drilling in 1960 and they finished, well, they claim on July 4th of 1966.
yeah. What was the US military doing drilling ice cores back then?
Well, the U.S. military was deeply involved in understanding climate change, and cold places in the 1940s, 50s, and 60s. And it was based completely on a strategic imperative to have control of the Arctic. And so when they realized that the climate in the 1940s was warming, the people in charge of military strategy hired physical scientists, glacial geologists, people who study ice, to understand climate over time. And one of the things that one of those men, a fellow named Henri Bader, suggested is that we could figure out the history of Earth's climate by looking at ice and treating it like a sedimentary rock, like a layer cake. And so he pushed for the drilling of several cores, of which the Camp Century one was the final and the first core to make it all the way through an ice sheet, almost a mile of ice. And it got to the bottom and they kept on going.
It kept on going down into the bedrock.
Well, not necessarily bedrock there, but they
Oh, you
kept
mean
going.
kept on going to other ice samples?
They kept going below the ice and into the frozen soil below. So they brought back 3.5 meters, 11.5 feet of frozen soil. Until recently, no one had ever performed that feat again. Pretty amazing technological advance for, well, you can look at me, I'm not young. And when that core was finished, I was 5 years old.
Were
So
you
that,
part of that process? Were you there drilling?
no, I was not. I'm sure I
Okay,
was chasing
you're
my
not
tongue.
that old.
I'm chasing my Tonka toys around when that was finished. I am absolutely sure. No, so I think it says a couple things to us. It says that understanding climate and understanding how it's changed in time is an absolutely nonpartisan issue. It's something that an organization as conservative as the U.S. military was interested in, and it can be looked at, in my view, as an operational issue. Operational for society, operational for the military, a very practical issue, and that's the way the military approached it.
Absolutely. And they're still engaged with climate issues. Richard, I know the Army Corps of Engineers is already planning to spend hundreds of billions of dollars to protect 3 US ports. How important are these ice core studies to those Corps of Engineer projects?
Yeah. So the whole picture really matters. And it is the understanding of the history of the ice, it is the understanding of the present of the ice, and the understanding of the future of the ice. We know that um, we're seeing flooding along the coast now. I often show pictures in my talks of a no wake zone sign sitting in the middle of a street in South Florida, surrounded by water on a high tide day. And I show pictures of salt water washing around the pillars supporting a parking garage next to an octopus that swam into the parking garage on a high tide day. We already have impacts and they're going up. And the Corps of Engineers has been charged by our government with protecting cities. And so they have said we will put plans out that the public can look at, and you can find these reported in various and sundry news outlets. The Ike Dike for Houston was listed in one publication as being $57 billion, 52 billion for a Sandy Shield for New York City, another 120 odd for protecting San Francisco Bay and the port, and we're up to 230 billion for 3 cities. Guiding that matters. If they are building for too much sea level rise, they're going to waste a lot of money building. They're going to lose ecosystem services. They're going to lose recreational services. If they're building for too little and they don't respond rapidly, the flood goes over the wall after it's built and it takes out what's behind the wall and the new things that are built behind the wall. And you have Katrinas in New Orleans happening over and over again along the coastline with huge loss. So the value of knowledge, of knowing what could happen, is really, really high. Scientists are dirt cheap compared to Katrinas and Sandys.
So basically saying that the science, the work you're doing and the other scientists are doing in these areas is crucial, not only to us individually, but, to our ports, to our commerce, to our military.
It certainly you can put a price tag on what specific protection actions cost, and you can very clearly see that if we build the wrong thing, that a lot of that money is not optimally invested. And when you start talking 230 billion for 3 cities, the value of knowledge is very, very high.
And that's just 3 cities. I'm seeing
Yes.
136 port cities around the world that are threatened by sea level rise. You can imagine what those numbers must look like. So obviously your data is very important. Andrea, I know you work the studies of historical sea level rise and use those for projections, today's sea level. Do you feel like that historic data is a good estimate for sea level rise under similar temperatures today?
Yeah, so looking at past warm periods to understand how high sea level was and how much the ice sheets retreated is really important because we've never been around to watch the ice sheets retreat to volumes smaller than they are today. And we don't have a full understanding of the physics involved in that rapid or dynamic retreat. So one way for us to calibrate our ice sheet models and have a better estimate of what's going to happen in the future is to look to the past, because to some extent, the Earth has done this experiment before. Not exactly the same way, but temperatures have been warmer and the ice has retreated. And so we can look at that to understand how much and how fast. And that's been really important for calibrating some of our models. But I actually think that a lot of the work that has been done has been underestimating how much those ice sheets might retreat under those temperatures. So I'll give you an example. I study a lot of what I study is a time period known as the last interglacial. So before the last ice age, there was a warm period. And global average temperature was at its highest about the same as where we're at today, more or less. And so we can look at that and say, okay, at that temperature, how much do the ice sheets retreat? And use that as an estimate for how sensitive those ice sheets are to warming. But what we've learned by studying this past warm period is that it warmed first in the southern hemisphere and then later in the northern hemisphere. So the ice sheets were retreating out of phase. They weren't going at the same time. So what that means, if we're raising temperatures at high latitudes at the same time, like we are today, because of the greenhouse gases that we've put in the atmosphere, we're warming both of those poles simultaneously. You would have to then add the contribution from Antarctica and Greenland together, which means you may be underestimating how much sea level rise will happen in the future if we were just looking at that peak sea level in the past, rather than thinking about how much did Greenland retreat, how much did Antarctica retreat at when it was the warmest during that past warm period.
So underestimating these levels is obviously going to affect those billion-dollar projects Richard was just talking about.
And I'd add one thing to that, which is duration. And so that the time that we're studying is an interglacial farther back than what Andrew is studying, about 400,000 years ago, which is something called marine isotope stage 11. And it's been known from a lot of research from other people that it's a long-lived period of warmth. Again, about the same temperatures that we've reached right now, but the sea levels were likely much higher than they were 125, 130,000 years ago. And so we know duration matters. And the other thing we know is that the carbon we're putting in the atmosphere today is not going to come out of the atmosphere very quickly by natural processes. And so the more carbon we put in now, the longer this human-induced heat wave is going to last. And the longer it lasts, the more ice we're going to melt. And I think that, to me, although it's far beyond any of our lifetimes, that to me is the scary piece of this, is not only do we have to first decarbonize and stop putting more carbon in the atmosphere, but then we have to figure out, if we want to save this ice, how we're going to get it out. And that's a real engineering challenge, and it's one that's going to require a lot of energy and a lot of money. And to me, it's the best argument I make to my students of the sooner we can turn this around, the better, because it's going to be cheaper. And it's the same thing Richard is saying. Once we understand how the system works, we can understand how to optimize and lower the costs of actually fixing the problem.
Richard, we'll talk a little bit about these ice sheet models, the prognostic models. Do they take into account all the processes that could contribute to sea level rise from ice sheet melt?
Right. So the simple answer is most of them are missing something that we don't understand well. So the very skinny version, if you wanted, think of a pancake. If an ice sheet is a 2 mile thick, one continent wide pile of old snow squeezed to ice under the weight of more snow and spreading under its own weight like a pancake spreading under a griddle. And its spreading rate depends on whether you sprayed the griddle with the lubricant before the oil before you put the pancake batter on, whether the bed is lubricated. It depends on how strong it is itself. It depends on how bumpy it is. Is it a waffle iron rather than a griddle? And it's these just giant masses spreading down to the coast. They also depend if you've got a pancake dripping off the edge of your griddle, you can hold it back with your spatula. We have floating extensions called ice shelves that hold back the spreading pile. And so a big prognostic model needs to get how much you're adding on top, how much you're melting on top, how rough or bumpy the bed is, how well lubricated the bed is by mud or water, how these floating extensions are interacting with the sides of the fjord to generate friction to hold it back, how the ice breaks off the front of that, how the water from the ocean is sneaking under the edge when the tide rises, how things break off. And a lot of this is not yet well observed. No sane human being would drive their snowmobile down to the edge of the ice sheet in the most interesting places because you would fall in a crevasse and die. And so there's real serious difficulty in observing a lot of these and trying to get hundreds of miles, sometimes under a floating extension with a remotely operated vehicle and not have it get crushed or lose its way. And so these things are not well observed. And then the modelers are faced with this horrible dilemma. Do we leave it out? Do we put in something we don't really believe, but we know the process happens, but we can't quantify it well? What do we do? And so the uncertainties are very large because the field glaciologists are still very constrained in getting out there and learning what we need to know.
So in general, these undocumented processes, um, leaving them out of the prognostic models, does that tend to overestimate or underestimate sea level rise?
A whole lot of these processes are positive feedbacks. They speed things up. So leaving them out would tend to underestimate. There's a
Underestimate.
few things I could make you very long lists of these are the things that lead us to overestimate. These are the things that underestimate. I think the underestimate list is longer right now.
It's interesting. I heard the same thing from Andrea there. The historic studies tend to underestimate. So I'm hearing in general, we're underestimating sea level rise. I see heads nodding, so I'm going
Yeah.
to run with that. So a lot of good science. I mean, the best we can do there. Um, I don't want to get too political, but you know, the interaction with politics and funding obviously important to our science. I'm curious how treaties like the Paris Climate Accord is affecting your research. You know, is it adequate? Is it missing the mark? How's that working? Paul, what are your thoughts on the Paris Climate Accord?
I would say less on the climate accord and more on the support for basic science and understanding how the Earth works and how the atmosphere works and how the ocean works. And I wrote a piece that was, I would say, or I tried to be as apolitical as I could about 3 weeks ago on the value of the National Science Foundation and the fundamental research that has been done for 75 years in that kind of environment. Because much of the research that it's going to take to continue to, as Richard says, refine these ideas so that we don't waste tens of billions of dollars doing something we don't need, comes from research that the private sector is simply not going to pay for and that is for the common good. So I think I would argue that less, I guess my research is, I can be direct. I can say my research is not affected by climate accords of any kind, but my ability to contribute to society in terms of understanding the history of Greenland's ice sheet and how it could impact coastal regions around the world has absolutely been paid for by the US government through the National Science Foundation. And it has paid not only for that research, but for training the next generation of students. So in my 30 some odd years of doing this, I've trained 45 students who have gone on to careers in science. And so there's this multiplier effect of when you train students in how to do this work, that becomes the next generation answering those hard questions and those pieces that Richard said we don't actually have well constrained right now. Those are the women and the men who are going to go on to constrain those pieces that is beyond our scientific lifetimes, right? So I think that the investment in basic scientific understanding pays back many times over. The estimates for the National Science Foundation of quote return on investment. So you put $1 in, how many dollars do you get back? Is something between $1.50 and $3 back. So it's a positive investment. The money that taxpayers in the United States put in pays back over time. And I think for something like climate adaptation, where we're trying to understand how many cities need to be protected, how big do the seawalls need to be, I bet the payback is a lot higher than that because of the damage that would happen to those cities, the amount of real estate, people living there. So I think if you pull back from any political lens on this and you say, practically, how do we address climate change and how do we address the impacts of climate change, which is this idea of adapting to climate change? Having the fundamental research to do that responsibly, as Richard articulated, is absolutely key. So, the Army engineers in 1960 cared about how the climate and the snow were going to change. The Army Corps of Engineers today cares about how the sea level is going to rise, and they need the information.
Yes, they do.
So,
Andrea,
and to your question about how the like Paris Climate Treaty impacts our work, sometimes it can be complicated from a science communication perspective, because I think when people hear these targets of 1.5 degrees Celsius of warming or 2 degrees warming, they have this notion that, okay, if we can limit warming to that much, we'll be safe, right? And we'll avoid impacts from climate change. And I think it's really important to dispel that notion. We look around us today, we're already seeing the impacts. Richard already gave some very vivid examples of what we're already seeing in terms of coastal flooding and sea level rise. And the ice sheets are still equilibrating to how much we've already warmed the atmosphere, right? We haven't seen that full response yet. I liken it to throwing 2 large ice cubes into a warm room and sitting back watching what happens. We're in the watching what happens phase right now, right? So when we think about these treaties, obviously the less we warm, the better. We already touched on that in terms of the ice sheets. But we also have to realize, even with the amount of warming we've already done today, we're going to see a significant amount of ice melt that's going to affect billions of people. And it doesn't matter. I mean, today I'm sitting here in Madison, Wisconsin, and sometimes I have to explain to people in Wisconsin why they should care about sea level rise, right? It will impact me here too in many ways, right? If our coastal economy collapses, coastal real estate, right, that's going to affect the national economy. What about supply chains, all the goods we have coming through ports that are threatened by sea level rise? You said supply chains 5 years ago, people didn't know what you're talking about, but after COVID, now they realize what that means for their lives and how this can connect the dots of how that impacts people. So those are just 2 examples, but this is not just a concern for people whose house might get flooded, right? It's a concern for all of us, right? It'll impact all of us in a profound way.
indeed, look at the migration, the billions of people that may be moving to Madison.
I moved here from Florida, so I was on the front of that wave.
You're on the front of that wave. Yes, you are. The impact
Yeah.
for our food system. So it does affect everybody. And I'm hearing you say, so I mean, Paris climate saying, hey, let's achieve 1.5, 2 degrees Celsius. That's what we need. We'll be safe. I'm hearing you say that's not enough. That's maybe a false sense of security.
I
Right.
think
And I'm not saying it's not a good target, right? But yeah.
Mm-hmm.
Go ahead.
I'll add something to that. I think that the idea of thinking about degrees Celsius warming is too abstract. And I think we focus too much on that and not enough on the day-to-day impacts on people. And those day-to-day impacts, certainly sea level is the most visceral one. And there's a wonderful sea level viewer that NOAA has put out. It's a little dated, but I use it for teaching all the time. And you ask people where their favorite beach is, and you can zoom into any place in the country and you can start digitally cranking up sea level and watching areas flood. That gets visible gasps from 200 undergraduates in a class when they realize that their favorite beach is going to be underwater. But I think it's more than that. I think it's the 1.5 degree average temperature range. It doesn't matter very much the average person, but if you talk to somebody growing soybeans in the Midwest and you say they're going to be 5 more days over 100, or they're going to be 2 weeks more of drought, things like that that really that people can experience in their day-to-day lives. I think we as a science community need to be focusing more on those specific outcomes than these idealized sort of things that come out of treaties like that. And at least for me, communicating with hundreds of people after writing this book and talking about it, the conversations that come down to the personal seem to engage people a whole lot better than the conversations that are theoretical. And I think we have to engage people because the real issue is, as Andrea said, these are really big ice cubes, and they're not melting quickly on a human timescale. They're not the ice cubes that you have in your drink that in 10 minutes left out on the table on a hot day are going to melt away. These are ice cubes that are going to take many hundreds or thousands of years to melt away, and that's not a human timescale that we think about. So we have to work in a timescale that matters to people and sort of a personal importance that matters to people.
Right. But
Yeah,
you
Rich.
made the point very well in the introduction there, Bob. The costs go up faster than the temperature. The costs go up faster than the sea level. And whenever we stabilize it, we just miss something worse. So the faster it's stabilized, the cheaper the damage is, the less cost, the less damage. And it really is clear that it's not the first degree. Oh yeah, it wasn't that expensive. Let's have another one. No. Okay, the costs are going up a lot faster. This nuisance flooding on the coast now, you put up a no wake zone sign and you don't drive down that street for a few hours on the high tide. But I also show the headline from the Miami newspaper of it's almost up to the water supply. And now we're talking billions of dollars to keep fresh water going to people's taps in their houses rather than salt water getting in. So it's a nuisance. It's a nuisance. Oh my goodness, it's really expensive. So keeping the lid on the warming, keeping the lid on the sea level rise is highly beneficial.
Yeah, action's important. So, Richard, what are your thoughts on treaties like the Paris Climate Accord? Are they helping us, or are they just distracting us from the real problems?
Yeah, but it's above my pay grade.
Okay, that's fair.
It's very clear that a lot of nations, and including ours, have taken action to supply the knowledge that would help policymakers, and that a lot of this has been done under the heading of our agreement across the world to avoid dangerous human influence on the climate system. And that knowledge underpins the costs go up faster than the temperature. It underpins how much the temperature can go up. A whole lot of the science of climate change is really, really good. And the projections that were made when I was a student are certainly coming through. They were right. They nailed this. And so the by creating the situation in which nations have put together teams who have built models of the climate system, these things have done a huge amount to give the knowledge to the public and to the policymakers to make response possible. So in that sense, the treaties have played a major role in motivating changes that will help us.
But I'll follow up with Richard because you pointed out something really interesting earlier, that the relative costs of doing the science to refine our estimates are two orders of magnitude less than what the Army Corps is about to spend. And I think that's an important thing that gets lost on people when we're trying to shrink the size of government, make government more efficient. And yet this is a governmental problem. This is not an individual problem to solve. It's a societal, a communal, a common problem. That the cost of getting the knowledge we need to act efficiently is trivial
If
compared to
if
the damage.
if
Yeah.
just three ports really take $230 billion, and if building too much or too little is highly costly, and you really want that 230 billion for those three ports to be right, if they dropped 1% of that cost on our heads in our community right now, that would be $2.3 billion. We would have no way to spend that much money right now.
Right.
You know, a tenth of that would be a fantastic boost in the coming International Polar Year to get the next generation. It won't be me. I'm going to be retired, but to get the next generation going. It's you know, the idea that you spend 1% to make sure the other 99% are spent correctly would be an immense increase in the research we're doing.
Yeah, I think that is the most telling thing I've heard today. Um, it's
Yeah,
just,
but
it's,
partly to that point about, how much do we build, right, to adapt and what to expect is we also have to realize that we can't just engineer our way out of this, right? So, I mean, even if we had enough money, there's not enough large size earth moving equipment to do all of these big, construction projects that people have envisioned in all these different cities. And if you build a big wall somewhere, that water has to go somewhere, right? If you're pushing it out of one city, you're literally making the problem worse in the city next door, right? And pushing that water to the side. And so that's also an important thing to remember. It's not like, oh, well, we just need to know how much so we can build to adapt to it, right? We can't just, engineering can help us, but we can't just engineer our way out of this problem.
well, and I think about my early training on land surfaces and not ice, and we tried this with rivers, right? We tried this with the Mississippi and the diking, and all it does is end up making the areas that are protected by dikes more vulnerable to the really extreme floods when those break or they overtop. And it starved the Mississippi River Delta of sediment, and now we're losing land at a prodigious rate in the Delta because the sediment's not making it there. So these unintended consequences are really important, but I do think we're at the point where we have to think about adaptation to save lives, but we have to think about it smart. And you're completely right. We can wall off these cities, we can wall off New Orleans, but what's the point um, for that? And with the hundreds of cities that you started with, Bob, around the world, they're just not the resources to do that and the money to do that. And so that's why I keep coming back to, we have to figure out a way as scientists to communicate that decarbonizing in the long term is the solution to this, and changing our energy systems. I don't think we've been successful at that in the last 20 plus years since Al Gore first, had the inconvenient truth and rode up on that lift and showed us the increasing everything was going to happen. What can we do differently? I think is really intriguing to me in the next decade or two. And I don't have an answer, but I'm curious what you two might think.
You're listening to the Climate Hour. I'm your host, Bob Grove. We're speaking with Andrea Dutton, Richard Alley, and Paul Bierman about how melting ice sheets are drowning the world. Let's talk a little bit about the IPCC. I know they just released a new report, the sixth assessment report, the AR6. Andrea, that report talks about low likelihood, high impact scenarios. I mean, they use that phrase. How much attention should we put on those scenarios? Is that the best way to communicate uncertainty about sea level rise?
Right. This gets back to a point that Richard was making earlier, right? If we don't understand much about a process, do we just leave it out of a model, right? Because we don't know much about it doesn't mean it's low likelihood, or right, that it's a low probability occurrence. What it means it's unknown probability, right? But it's still potentially very high impact. And so sometimes when people see that label, they think, well, we don't need to worry about this high scenario because there's a low chance it might happen. Well, Richard said before, there are many more reasons why it might be much higher than we think, than lower. So we really do need to pay attention to that. And anyone who's in the business of risk management knows that you need to look at more than just what is the central estimate of all the scenarios. You have to look at the full distribution of that. And for sea level rise estimates, there's this very long tail of high-end estimates. And we need to worry about that tail, right? Because if we're in that tail, we need to be prepared for what's going to happen.
Yeah. The sort of quantified part of the IPCC projections of sea level rise A lot of it is really pound on the table near certainty. We're warming the climate. The warming causes the ocean water to expand. It takes up more space. We're warming the mountains. That's causing ice and mountain glaciers to melt, and the water gets to the ocean. And then the melting around the edges of the Greenland ice sheet is very, very clear. And those are most of what goes into these quantified projections from the IPCC that lead to almost a meter by 2100 under the stronger warming. The ice flow parts are a lot harder. In those quantified parts, with the almost a meter by 2100, Greenland loses 2% of its sea level equivalent, and Antarctica loses 0.2%. And so it's really, really hard for the future to be much better than what the IPCC said in this report. And it's fairly easy to be worse. Because if you're only losing 0.2% of your sea level equivalent, there's a lot more there that could be lost.
And I
As I was saying earlier, best case scenario is IPCC. And what I'm hearing here, that a lot of this is being underestimated. We should really prepare for worst case scenarios.
Well,
Paul?
I think there, yeah, both Andrea and Richard, I think, alluded to this, but that Greenland in particular and parts of Antarctica have this issue where we may cross basically a line of no return, where we're going to lose either part or most of the ice sheet. And that is, I think, a piece of science that's really uncertain right now, is how much warming can we tolerate before, and I know Greenland much better than Antarctica, but before the Greenland ice sheet gets small enough and low enough that it can no longer support itself and retreats into small ice caps in parts of the island. That could be catastrophic, not on an individual's lifetime, but certainly on sort of the century time scale or more in terms of sea level rise. And that's the thing I suppose it doesn't really keep me up at night, but intellectually keeps me up at night, is where's that boundary, and how long can we go on before we hit that? And we're not even going to know that we've hit it when we've hit it. And that's a thing I think that, people make all these medical sort of suggestions. Oh, well, my cholesterol is really high and my doctor tells me I should do something, but I'm just going to put that off. At what point do you make that decision that high impact event, coronary, in case of your high cholesterol, or Greenland reaching this tipping point where it's not going to come back? How much caution do you take as a global citizen, as a scientist, to say, hey, wait a minute, there's something really big out here, and yeah, even if that chance is only 5 or 10%, why would we risk that? And I don't think we have the science. I'm really curious to see what Richard would say. We talked about this maybe 5 years ago, but what he would say now about that, where that point is, and Andrea too, that
Yeah.
how far we can go in our current trajectory before we got to start worrying about it.
Yeah.
So
So
what are we looking
probably,
at?
yeah.
Go ahead, Richard.
So probably fairly close in Greenland. We
Mm-hmm.
can warm it up enough that if we keep the temperature up, that Greenland's in big trouble. And then there's the dynamic part in Antarctica. So if I'm not sure if any of you have had the wonderful experience of going to Glacier Bay in Alaska. Glacier Bay, when it was discovered by Europeans in the late 1700s, did not exist. It was entirely full of ice that was 60 miles long and a mile thick in the middle. And it was stuck in a bottleneck at the end. The ice was sort of wedged up where the seabed was high and the fjord was narrow, and it hung on and it hung on and it hung on. And when it got kicked out, it fell apart. John Muir actually watched the icebergs falling off the front and took useful data, and it just fell apart. Then it went back to a different bottleneck way back. And this is the way ice that goes into the ocean behaves. It gets stuck in a bottleneck. It hangs on by its fingernails. There's lots of processes to keep it there. If you kick it out, it changes really fast to a new state. And our worry is that Antarctica has a couple of bottleneck pieces that if they fall apart the same way that Glacier Bay did, the world will know. So, 11 feet of sea level or more. And so that's the real tough one, because the tipping point may or may not be tipped, and the difference between we tipped it and we didn't tip it is really big.
Yeah, and I
Right.
should say it's become really real for us in the last 5 years as we've worked on this Camp Century core, because sitting under that nearly mile of ice are perfectly preserved fossils of tundra vegetation and insects that lived there 400,000 years ago. You look under the microscope and that seed or twig looks like it could have come out of the pond in your backyard. And so that's a really visceral indication that massive amounts of ice, at least the equivalent of 1.5 meters of sea level, vanished from Greenland 400,000 years ago. So we know it. It's not a model. It's not a hypothesis. It's none of that. It's reality that Greenland can lose a large amount of ice. What we don't know 400,000 years ago is whether we lost the entire ice sheet or not. But there are significant hints that we did. There are also evidence that we didn't. So that's another piece that's out there. But the same fossils are present right at the center of Greenland ice sheet, a place called Gisp 2, where Richard was drilling when I was a graduate student. And the same set of fossils is there. That was tundra sometime in the last million years. So Greenland is a little more fragile than some of us might have wanted to believe a decade or two ago.
So Paul, we talking about tipping point on Greenland. What would that look like? I mean, if the ice was to melt, what's that effect on sea level? What's that going to cost us economically?
Oh, well, let's see. Greenland holds something like a little over 7 meters of sea level equivalent on there. So 24 feet. So again, my favorite way to reach people when I'm giving a talk about this is to say, I want everybody to close their eyes, and everyone's closed their eyes and they're looking at you. I'll open my eyes because I'm speaking. And I say, imagine your favorite beach, right? Okay, now imagine your favorite beach with 24 feet more water on it. And for my average student, that's what, 4 times, 5 times their height, right? And then I asked them to say what went underwater, and they're like, oh, the clam shack went underwater, or the bridge to the island went underwater, or the rock I used to hang out on went underwater. So we melt Greenland, the entire coastal geography that everyone on this planet knows is going to change. 25 feet, and places like most of Florida's underwater, right, Andrea? And
Yeah.
Boston is a couple islands, and New York is a few islands. It will just you will have to get a new globe and new world map. So it's a huge thing if we lose Greenland. We also lose what I call the giant, bright, shiny object in the Arctic. So that's the Wisconsin answer, right? So if Greenland loses its ice, all of a sudden you've taken this huge mirror essentially in the Arctic that is reflecting almost all the sunlight that comes in, and you've replaced it with dark rock or vegetation or water. Which is going to soak up most of the solar radiation, and it's just going to make it warmer. So it starts this feedback loop of the ice is going away and there's more dark surface and it's getting more heat and more ice is going away. We don't want Greenland to disappear because, it will affect the entire world in one way or another.
Yeah, Andrea, Greenland ice sheet.
Yeah, well, as Paul said, what happens in Greenland does not stay in Greenland, right? And the point he made earlier too is I say a lot, this notion of tipping points is that we're not really going to know exactly where that tipping point is 100% until we're past it. We can say, oh, there it was, right? Now sea level is right, 10 times faster than it was before. And you asked before, Paul, what do I think about how close we are? I think we're close enough in Antarctica to worry about it, right? And what's important here, something we've touched on a few times already, is that there's a lag time between how much we warm and how much the ice sheets melt, right? And so that's a reason for not delaying reducing our emissions. This is not something we can say, oh, well, let's just do that in 3 years or in 5 years or in 10, right? The sooner we do that, the more important that is because there's this delay time for the ice sheets. And so in the remaining, 3 or 5 years that you've delayed, you've already added that carbon to the atmosphere. You've already increased that warming. And so then you're committed to an additional amount of sea level rise, essentially, right? So this is one thing that's really important from a policy perspective as we move into the future is that the ice sheets are a great example of why the sooner we do it, the better, right? Anything that we do sooner is better.
And cheaper.
Yes.
And cheaper, yes. Jumping back to Antarctica, I mean, its ice sheets, how do they compare to Greenland? Richard, do you want to take that?
Right. So a lot bigger. It is so the total amount of ice in Antarctica converted to sea level. So what it can actually do, we split up Antarctica in sort of the Western Hemisphere part and the Eastern Hemisphere part. And the Western Hemisphere part is probably can raise sea level 3 or 4 meters. The Eastern Hemisphere part a lot more. The total number is something at about 57, 58 meters. So just a shade under 200 feet of sea level in Antarctica. We do not expect that anyone alive today would live to see most of that lost. But there's the 3 or 4 meters in West Antarctica potentially could go fairly fast. And there's a couple pieces that are a little bigger than that in East Antarctica, the Wilkes and Aurora basins, that also could go fairly fast. And so the total possibility, if Antarctica loses its ice shelves and if it retreats from its bottlenecks, then pretty rapid changes could happen that would be very surprising.
Yeah, and while we won't see that whole magnitude of sea level rise in our lifetime, it's an important point to remember that this amount of sea level rise that we're talking about, whether it's 1 meter, 2 meter, 3 meter, four, right, is not reversible on human timescales, right? It's much easier to melt that ice than it is to regrow it, right? And particularly with what we're doing to the atmosphere. And so that's another reason why, as you know, every extra amount of carbon we put into the atmosphere is committing us to that sea level rise, which we can't take back in our lifetimes, right? It's not reversible on human timescales, which is an important point to remember.
And I think the other piece to remember, if I put on my more of my geoscience hat, is that day to day, that small amounts of sea level rise may matter only marginally, but it's going to matter when that Category 5 hurricane hits. And the difference between flooding the subway tunnels in New York, Boston, Washington, D.C. is inches. And as what Richard said, then the damage goes up exponentially. So I think it's very easy as an average citizen to look and say, 5 millimeters of sea level rise a year, why should I care about that? But it's the accumulation of that rise over decades and then the extreme event on top of it that is going to cause the catastrophe.
Yeah, the extreme event, or just reaching a point where the infrastructure can't handle it anymore. So you mentioned before, like losing freshwater supply in Florida, right? So if it just gets high enough that stormwater can't drain off anymore because it's a gravity-fed system, right? And so there's a big problem. It has nowhere to run to, and so it will just sit there in the streets. So, right, as you say, it's a slow-moving problem day to day, year to year, but those impacts can be profound once you hit that another type of tipping point in terms of infrastructure, where there are huge and domino effects.
And I think you can also spin it back to the military in that I think something like 5 of the US 12 aircraft carriers are at Newport News, which is already suffering from high tide flooding and storm flooding. And so the US military, particularly the Navy, is really concerned about this and how they're going to adapt to service their massive fleet around the world as the sea level goes up.
The point's very clear.
Go ahead, Richard.
Yeah, I was going to say when we did our PBS miniseries, and more than a decade ago now, the problems of warming in part were explained by a rear admiral in his dress whites who told us how the military's concerns were, and very broadly in a huge number of ways, that this is a national security issue.
Andrea, you were talking about these melts. You know, these are permanent. I mean, once it's gone, it's gone. I mean, ice sheets can recover. I read that if we could move back to pre-industrial temperature levels, if that's possible, if we did that, how long would it actually take for the ice sheets to recover? Do we have any idea?
I mean, we have some idea by looking at the past of how long it takes to grow an ice sheet, but we can't do that under just going back to pre-industrial levels, right? We would have to lower it even more. So that's part of the challenge too. So it's again, it's not easy to make this go in the other direction. even when you start getting into hundreds of years and thousands of years. So that's more reason that we shouldn't throw caution to the wind.
And again, if we
Well,
look at nature for the last million years, the cycles have been 100,000-year cycles of warm to cold, warm to cold, warm to cold. The slide into cold takes the bulk of that 100,000 years, and
Mhm.
what's called a termination, the warming, is incredibly rapid. It might be what, 10% of that 100,000-year cycle. So if we take nature as an analog, Andrew is completely right. It's going to take many times longer to get that snow and ice back and out of the ocean than it did to melt it.
I keep reading that the safe limit for ice sheets is 1 degree Celsius or lower. I mean, it is. I'm hearing that that's probably not enough.
At 1 degree Celsius, we lost a large volume of the alpine mountain glaciers. They don't
Mm,
contribute, well, they contributed a lot to sea level rise early on. Now they are a smaller portion as Greenland is melting and that the
yeah.
ocean itself is warming and expanding. Um, I don't know that there's actually a safe number. I don't know how you would define a safe number.
Yeah,
Yeah.
the problem with the notion of safe is that it requires you put some value judgment on it, right?
Mhm.
And what do you consider safe? Who is safe, right? And so that's a very difficult question to answer when it's framed that way. So I guess it's easier for us as scientists to talk about just how much, that would mean in terms of sea level rise and ice sheets, but those impacts are not felt equally everywhere. And I think that's something also very important to this conversation about sea level rise is that, a lot of the adaptation that's happening is at the local level. And those are communities that maybe have the money to put into those adaptations. Communities that don't have the money can't build a wall, right, to save themselves. But the community next door maybe has built a wall and it's made the problem even worse than the community that can't afford it. So there's a real socioeconomic imbalance in terms of ability to adapt and who's going to be affected by this. A lot of communities were built in areas that were red line districts of not as desirable land, which often were low lying areas, right? Whether those are inland cities or coastal cities. And those are likely to get flooded first. And so there's another layer of complication when you're thinking about what's safe or what's acceptable, right? You also have to think about who's being impacted first. And not everyone can adapt just because some people can.
So Iceland and Greenland, huge ice sheets, obviously critical, especially if they reach a tipping point. I'm curious about other glaciers around the world. Richard, besides Iceland, Greenland, what's the most critical glacier in your mind?
Yeah, the mountain glaciers, if we continue to drive warming, the picture's clear, they melt. And we will have relatively little ice left in the path that we're headed on. Very little, as you go up, the peaks get smaller and smaller, and the little tiny area right up at the top may keep a few glaciers, but most of them are in trouble. This is for sea level. There's only, this much or so sea level left in mountain glaciers, a foot to 2 feet, something like that. But it's hugely important. The water supply really matters to people. We have fisheries and agriculture and recreation and drinking water that have relied on the summer supply of meltwater from glaciers in large parts of the world. And when the glacier is gone, then that summer supply is also gone. So they're sitting there serving as reservoirs that nature gave us and we didn't have to pay to build. And they don't evaporate rapidly from the surface the way real reservoirs do, and they don't leak out the bottom or any other problems like that. So there's real issues in the loss of them. There's a lot of local hazards issues. If you have a very steep hillside on a valley, but the valley is full of a glacier, you can't have a landslide that buries a town. If you melt the glacier out, now you have a slope there that can make a landslide. The landslide might go into a lake that the glacier left and cause a giant flood, which sweeps down the valley. So there's a lot of hazard issues. There's a lot of water issues, many water issues that involve rivers that flow across borders between countries who sometimes don't like each other and have big bombs. So there's other interests that come into this that go a little beyond my expertise, but are important.
And certainly, I spoke to a brigadier general a few months ago about glaciers, and the takeaway was that China invaded Tibet to get control of the Himalayan glaciers because that's their water system that feeds their entire agriculture. You know, without those glaciers, suddenly they have no food. And am I hearing that the glaciers are probably more exposed to elimination than the ice sheets at this point? Are they going to be the first thing that goes? I'm seeing a
We're
lot of head
certainly
nods,
more
yes.
confident, yes.
Yeah, so once those glaciers are gone, then suddenly we don't have water for our food systems. And obviously, what does that do to the planet? What does that do to all of
Yeah, I
us?
think it's they're small, so they're more vulnerable, and
Mhm.
they work on different time scales. But I think they're also geographically isolated. So the bulk of the United States does not have mountain glaciers, and the bulk of the people here in the United States don't depend on them for water. But if you go to some place like the Peruvian Andes, they're incredibly important to the communities there. So again, as Andrea said, there's a whole disparity between people in the world and how the loss of mountain ice is going to affect people and how it's integral to their cultures and their survival. Um,
Let's talk about solutions. I mean, I don't know that there are solutions, but I think each of you have an idea of what you would like to see done to improve this condition. So let's just go around the room and talk about best solutions. Richard, what are your best solutions for climate change?
Yeah, building a sustainable energy system is right now the the scholarship that I'm reading says that it's cheaper to build a sustainable energy system than it is to double down on the one we have now. It's cleaner. It will bring more energy to more people for more time so that people can do the things they want to do, and we can build it in a way that doesn't change the climate. And so that would be the top of my list is to get the bright students here building that sustainable energy system that'll power everyone essentially forever.
Andrea, what are your best solutions?
Yeah, I 100% agree with Richard, and the point of doing that is to reduce our greenhouse gas emissions, right? So any way that we can do that, and I think sometimes people look at that and say, "Oh, it's huge, it's a big problem, it's bigger than me." Look at it on the flip side. There are so many different ways we can do that. There are things that we can do on the individual level as well as the collective level. And so that should be empowering to us, right, as we move forward. Anything that we can do to reduce our emissions is good. And that's where I would put my money in terms of what we should do in the future.
And Paul, what are your approaches to improving climate change?
I completely agree with Richard and Andrea that decarbonization is the one thing we have to do. I think the question for us as scientists is how do we communicate in a way that is more effective than we have in the last 20 or 30 years about climate change? I don't have the answer to that, but I've been thinking an awful lot about it because I've been teaching climate for the better part of those 20 years. And I don't think I've gotten it right. And I'm just struggling with what do we do as a group of people to get beyond the group of people we normally talk to, right? And to make it clear that climate matters to everybody on this planet, decarbonizing matters to everybody on this planet. How do we get beyond this current hyperpartisan divide, which isn't serving any of us well, to a rational approach to, as Richard started the segment with, the cost of inaction is huge. The cost of action could actually be far lower than the cost of inaction. And so I think we need to get away from the scare tactics of the sky falling in when students ask me that, which started the climate movement and continues in parts of it. But I think we need to come to a very practical, rational approach to costs, benefits, and a broader societal impact, and keep talking about it. Get out of our white lab coats and talk to people.
And that's why we're here today. I agree with Paul. Climate communications is probably the most important thing we can do right now, just to bring people to the table and allow for that electrification, the renewable energies, all those things. So thanks for that, Paul. Let's go around the room again. Talk a little bit about your work, your books, websites where people can go to learn more about what you're doing. Anything you want to share with our listeners, Paul?
My work in the last half a decade has been really focused on Greenland. It actually started with Richard and a visit 20 years ago to the University of Vermont. So I'm at the University of Vermont. I've just published a book called When the Ice is Gone. It's about Greenland, it's about climate, it's about sea level rise, it's about history, it's about the military. And it is absolutely directed at the average citizen, not at scientists, because I wanted to make that connection that I've been talking about today. And you can find me or find more about me at my website at the University of Vermont.
Thank you, Paul. Andrea?
Yeah, well, most of my work has been looking at past sea levels. I use fossil corals to track the position of sea level through time. And so I've given lots of talks that are online for that. I haven't written any books yet, like the two of you have. Maybe I will someday. But if you want to learn more about the work that I'm doing and continue to do, you can also find more on my website at the University of Wisconsin in Madison.
Thank you. And Richard?
Yeah, I started working on glaciers the summer of 1977 as a summer job with Ian Willens at Ohio State. So I've been doing this forever, and now I basically answer email and I don't do much, but I work with a remarkable team of researchers and grad students and undergrads at Penn State, and I am deeply proud to sing their praises loud and long. They're doing great things. So you can look us up at Penn State. If you look for my name, you'll find a path through to it. And I try to get out and chat with people about the opportunities that are available in solving this problem. We get something better than we have now. And we can get more energy for more people with less impact to allow them to do the good things that they want to do. And we can do it at a lower cost. And so the opportunities to turn our engineers, our scientists, our materials scientists, and our business people loose to build something better it's just fantastic. So I'm cautiously optimistic that we will build a better future.
This has been a great conversation. Thank you. And thank you to our listeners. We welcome your questions and feedback. You can learn more about the Climate Hour at climatehour.net. That's climatehour.net. This is the Climate Hour. I'm your host, Bob Grove.